Hi, it's James here, and I'm just going to do an introduction to calculus, known as rocket science, and you'll see why later on. It's easy when you know how, and this is how. First of all, what we're going to talk about is like graphs, but I'll do it quite quickly. So for any system, we put something in, something happens to it, and we get something else out, like in a factory or with numbers. So that's what we usually graph. So if you have an input number, which is a known number, we know what it is, and we can choose it. We put it into like a magic function box, and the function box does something to that number, and we get a different number out. The function that happens to the input is always the same for any input, so it has to be fair. So it'll treat every number the same. For instance, if you put a number in and the function is to add 2 to that number, it'll add 2 to everything that you put in. If you put a number in and you ask the function to multiply it by 10, then whatever number you put in, it'll multiply by 10. So a function is just something that happens to your input and then you get something out. This is written as the output is a function of the input, and that is written a lot of the time as y equals what they say f of x. Y is f of x. All that means is you put a number in, something happens to it, and you get a different one out. So that's all it means. So don't worry too much if you're confused about the notation. So this is just another slide showing it. Put something in, something happens to your number, you get a different one out. But the same thing happens to every number that you put in. It's just the numbers you put in are different, aren't they? Think of the numbers on the number line as being x. And then we plot the relationship between the output and input on a graph using the Cartesian plane. That's named after René Descartes, who was a philosopher and mathematician. So all the Cartesian plane is the xy plane, things that we plot graphs and coordinates on. So that's what it's called. And if I was to ask how steep is that half pipe, if you were skating, really, you want to ask yourself how steep is the half pipe, but really you can't really answer the question because it depends on how far along it you are. Where you stood on it is going to have different steepnesses. So you've got the vertical part on the left, so it's completely steep, and then it gets less steep as you move to the right, and then in the middle it's flat, and then it gets steeper again as you move to the right even more. So with the half pipe function, the slope changes depending on where you are. Now imagine that we've got a graph. This is like roughly like it's kind of like a graph of x times x, or a graph of x squared, and it's a little bit like the half pipe. Imagine you're stood at point A and you're trying to figure out how steep the slope is. Well, you could use a big long measuring stick or something, and you'd have to put the other end of it up on the side of the half pipe, but that won't show you how steep it is where you're stood. So the distance along the bottom between where you're stood and the other end of your stick is called dx, and if you look, every time you move the point B closer to where you're stood, dx decreases, and the slope of what we call the secant line, which is the line that cuts that curve in two places, that slope of the green line becomes ever closer to the slope of where you're stood at the time, at point A. So here B's got even closer to A, so dx, the change in the x value between A and B, has got smaller, and you can see the slope changing of the secant line, and eventually when dx, the change in the x value, gets like almost to 0, we call it a tangent line. So the secant line doesn't cut the curve anymore, it just touches it, and the slope of the tangent line is equal to the gradient of our function. And that is what differentiation is. It's about finding a slope of a function nearly at an instant in time. There's a couple of websites that you might want to have a look. The bottom one's on the gradients, and the top one is about secant and tangent lines, so I'll just go through that now. So this is on desmos.com a graph of y equals x squared, or we've put a number in x the function as timed x by itself, and you get square numbers out. And here is point B, this is point A. If you stood at point A and you want to find the gradient of the slope, it's just like what we were doing before. That is the actual slope at point A. As we change the distance between point B and point A and we make dx smaller, as we reduce the distance dx down to nearly 0, the secant line becomes a tangent line, and that is equal to the derivative or the gradient of the slope at point A, so it's more accurate. Here's a few more websites which are really good for showing this. You may want to note them down. They are case sensitive, make sure you type them in correctly. And this is just the same thing, but the slope of a function, or the gradient, is called the derivative. It's showing how one thing changes compared to x changes. It shows how the output changes compared to the input. And the slope is the way that the eyeball is looking at the time. So here, when x is -4, the gradient is very steep, but it's negative. Here, x is -3, it's not as steep, it's still negative. Here, the gradient is a very small slope, still negative. And when x is 0, the gradient is flat. So a flat line has no slope. So it has no gradient, or the derivative, as we say, is 0. And here the gradient is increasing, and it's positive when x is 2. And when x is 3, the gradient is very steep and positive. So what we can say from that, like, even though we've plotted the output y against input numbers we put in x, so y is a function of x, y depends on what x is. So the output is a function of the input, and the y value depends on the x value. But what we just saw with the gradient or the derivative, the slope actually also changes as x changes. So the derivative itself is also a function of x as well. And some of the notation you'll find, if the output, say y is a function of x, like we always say, all that means is y is something done to the number we've put in. Then the first derivative we call dy dx, or f prime of x, or y prime. All that means is we've differentiated it once, we found the slope, and then there are the other things we can do. We could differentiate again, but we'll come on to that later on. Some of the notation to get used to, you know, you've got y is f of x, or it could tell you what the function is, like y is 3x squared, or x squared, or x plus 2, or whatever. And it will also write it as y of x, or it could write it as a function of x, f of x. So you get all these different ways of writing the same thing in maths books. And there's all different ways of seeing the first derivative as well, like y prime, or f prime of x, y prime equals 6x, y prime of x equals 6x, function prime of x equals 6x. It's just all different ways of saying the same thing. So whenever you see the little apostrophe, or you see dy dx, all it means is it's been differentiated. They found the slope at a certain point, or they found the slope generally for all values of x. So I hope this has been a good little introduction to differentiation, and we're going to carry on with lots more videos. Okay, thanks.